Okay, we're going to do some practice with modeling and then section 2.7. This section, these notes are both in Canvas under Files. I'm labeling this as section 2.6.5 because it's in our curriculum to be in between 6 and 7. So, we're going to do some problems that show up a lot in calculus, and that's why they have us introduce them to you here. So, gardener has 140 feet of fencing to fence in a rectangular garden. Find the dimension of the largest possible area. Let me make sure I'm recording. Yes, I am. All right. So, what's happening here? We have 140 feet of fence, and we're making a rectangle. So, I'm going to go ahead and draw a rectangle. And I'm not going to worry about it being to scale because I don't know how long it is yet. But what you generally want to do with these is you want to say, well, what do I know? And what do I want? Well, I know that the perimeter has to equal 140. And I have a formula for perimeter is 2 length plus 2 width. And let's go ahead and label these L and W for length and width. I want the max area is given with length blank feet and width blank feet. Given by, maybe given by. I'm not sure about the vocab. I think that sounds better. Yeah, with word problems, I like to go ahead and write the answer first and just put in a blank so that I can keep track of where I'm going. So, okay, I want area. Well, area equals length times width. So, here's the trick, is that we want to use this function, this area, and maximize it. The problem is that it has 2 variables. And we're not really prepared to deal with having 2 different input variables. So what we do instead, we say, well, let's use what we know. We know that 140 is 2L plus 2W. So 70 is L plus W, which means length is 70 minus W. And so I airlift that over here, and I say, okay, that means area. Let me move that up a little. This is probably unnecessary. I'm making this harder than it needs to be. Area is length times width, so then area is 70 minus W times W. And so we want to figure out what is the maximum of this. What is the largest this could be? And well, I know what this looks like. This could also be written as 70W minus W squared. Either form is acceptable. But if I use the first form here, I say area equals 70 minus W, I can say, well, there's an x-intercept at 0, 0. And there's another x-intercept, if this is W and this is A. There's another x-intercept, or or W-intercept, I suppose, because it's crossing the W-axis, at 70, 0. And it goes up and back down. And by inspection, or by knowing how quadratic equations work, you can say, well, it must be in the center. And this is true for parabolas, that if you know the 2 zeros and the vertex is exactly halfway between them. And so from that, we can say, all right, if I want to know what the area actually is, I would plug it in here. What is A of 35 would be 70 minus 35 is 35 times W, 35, which is, so 35 feet, and the area would be 35 squared, which is 1225. Though technically it didn't ask for that, just ask what dimensions would give the largest area. So the largest area is in fact a square. And that's the standard solution to this. And you could kind of, if you want to try it, you might find it interesting. Take this piece, cut it off, and move it up here. Yeah, I'm not trying this to scale. But the idea here is that you've got this missing piece here. If you were to take this inner part of the fence and flip it over that way, you would not increase the perimeter, but you would increase the area. And so because of that, the square is the largest rectangle by area. And we can do that because this is a quadratic. If this were not quadratic, if it were a more complicated function, we'd need a somewhat more complicated method to figure out where the max is. But this is still how we would set it up. See, we said this is a function of two inputs, length and width, but really there's only one. And the reason is because of the way the perimeter is defined, if we know the perimeter and we know one of the sides, then we get the other side for free. So once you know the perimeter, there's really only one variable in this equation. All right, let's do another one. The next example. It's a can. A manufacturer makes a can that holds 1 liter. What dimensions use the least amount of metal? So, I will give you the vocabulary here, although I won't insist you use it in this class. But we would say the objective function is a thing we're trying to find either the max or the minimum of. And the amount of metal, well, what is that called mathematically? It's called the surface area. Surface area is defined as 2 pi r squared plus 2 pi r h. You can see that if you were to imagine the can, the top is a circle, the bottom is a circle. Those are each pi r squared area. The rim is a little harder to see. What's its surface area? What you can do is you could take a can with a label, and if you were to peel the label off, you would see that it becomes a rectangle. And so I would encourage you to try that. If you've got a canned food label in your apartment or wherever, dorm, try to peel the label off and you'll see it becomes a rectangle. This is height of the can. And then what's the width of this rectangle? Well, it would be how far it is around one of these circles, which is 2 pi r. So 2 pi r h is the area. So that's my surface area formula. Now the other thing I need is a constraint. They say, what is the can that uses the least amount of metal? Well, a can of volume 0. That would be no metal at all. But we are told that the volume is in fact 1,000. And so, once again, we're going to try to use this constraint, this set number we're given, to get rid of one of these variables. So I say, well, it's a cylinder. The volume is pi r squared h. So again, if you look at the picture, it's the area of the base times the height. That's how you calculate the volume. So, we say, okay, I see this equation, I'm going to solve for h. I don't want to try to solve for r because then I have to deal with that plus or minus stuff, and I don't want to. So I'm going to say h is 1,000 over pi r squared. I guess you wouldn't use plus or minus because volume is positive, but you still have a square root, and those are hard to, those are annoying. So then the surface area would be 2 pi r squared plus 2 pi r, and then replace the h with 1,000 over pi r squared. So that's 2 pi r squared plus, oh, the pi's also divide out, I suppose, 2,000 over r. And so now, like I said before, finding out where this is a max, or minimum, I guess, in this case, is not as easy because this function is more complicated. And so, yeah, I would say type this into some graphing software and look, and you can find there's a minimum here. And you just type whatever, find out whatever that is on Desmos or whichever program you use, and you would just write that down. Now, if you go on, when you go on to calculus, I say when because I assume anyone taking this class intends to take calculus, you would figure out how to do this directly. So this is a calc preview, which is, you would say, I would try to calculate the tangent line, that is, say, a line that's just lying right along the graph, and that would be using that difference quotient that we introduced. And if you find a place where it's 0, that means it's horizontal, because at the bottom of this curve, it's neither increasing nor decreasing, it's flat. That said, that's not a pre-calculus problem, that's a calculus problem. So for this class, you need to be able to set it up, you need to be able to write out what the objective function is, what the constraint is, and you need to replace them. You need to know how to use the one there, you know exactly how much it is. In this case, we know exactly what the volume is, to replace one of the variables in the other function, the one we're trying to make as small as possible. But once you get that function, unless it's something simple, we're not going to ask you to actually find what the max or min are by hand. We're just going to say, that's good, you can check the graph. But yes, finding maximum and minimum is one of the 5 big problems that calculus was invented for. Okay, so let's see what's next. Alright, so that's the couple things in modeling. That was page, I think it's 237. It's listed in the syllabus. I can't remember exactly what page number it was. But we're going to talk about combining functions. So, how do functions work if we want to combine them? So, what happens in a lot of math is we start with simple objects and we say, well, what are the objects that work on those objects? So, we have numbers, we have real numbers, and we have functions that do stuff to numbers. But what if we then want to do stuff to functions? So we need to define what it means to add, subtract, multiply, divide functions. Now, there's a few ways you can answer that question. But the simplest one would be called pointwise, which is to say, if we want to know what is f plus g of x, we say, well, let's go to x, let's plug in x to f, plug in x to g, and add them together. Same with subtraction, same with multiplication. You would plug them in, you would add them together, or subtract or multiply. Domain would be the intersection of the two original domains, meaning if you can't plug in x to one of these functions, then it's undefined for one of them, so it'll be undefined for the combined function as well. And so this is, like I say, it's the simplest way to find it, because now we said for everything that's in domain of both a and b, we now know what this function, these new combined functions, do to it, so therefore that is a new function. Now, the one trick is when you divide functions, as we've said plenty of times, you can't have a zero denominator. So if you have a 0 denominator, you have to cut that out of the domain. So yeah, domain restrictions, whenever you combine functions, x has to be in the domain of both individual functions, and if there's a denominator, we have to make sure the denominator is not 0. So let's see some examples, or an example. There are more in the book. Let f of x equals 1 over x minus 2, g of x equals root x. Let's find the combined functions. So we say, okay, so f of x is x squared. G of x is... Wait, am I on the right? Oh, let me make sure I'm at the right... Oh, sorry, I'm looking at the wrong problem. Yes. Excuse me. F of x is 1 over x minus 2. G of x is square root of x. So f plus g of x is 1 over x minus 2 plus square root of x. F minus g of x is 1 over x minus 2 minus root x. The domain of each of these, well, now let's do f times g of x would be square root of x over x minus 2. I just multiply them together. The square root of x ends up on the top. You separate this out so it doesn't run together. Okay. Domain for f is negative infinity to... space. Domain for f is negative infinity to 2 union 2 to infinity. Domain for g is 0 to infinity. So the domain of each of these three is just the combined domains. I know there's a denominator, but that's already taken care of when we did f. So domain for each of these would be negative infinity to... No, hold on a second. No, that's not right. Not negative infinity. The square root starts at 0, so the domain of the combined function would also have to start at 0. So it would be 0 to 2, parenthesis, union 2 to infinity. Now, f divided by g is different because we also have to make sure it's not 0. F over g of x would be 1 over x minus 2 divided by square root of x, which we rewritten as 1 over square root of x times x minus 2. And then the domain, it's similar to the other one, but now that we've got a square root of x in the denominator instead of the numerator, we have to cut out 0. See, 0 is allowed in f times g because it was on top. But on bottom, that's not allowed. So 0 to 2, union 2 to infinity. And then if you wanted to put these into a graph, let's look at one of them, for instance. Go to Desmos, and let's just 1 over x minus 2 and square root x, and then let's say let's do the minus 1 over x minus 2 minus square root x. So you pick any point here. Square, here we go. There's this. Let's see. The green is supposed to be red minus blue. So, hey, here's where red and blue are equal. And if we go straight down, we get 0. Because red minus blue, since they're equal, they'll be 0. Over here, the blue is above the red. So green is negative because green is blue minus red. Over here, the blue is above the red. Is there anywhere the red is above the blue? I guess over here for a little bit. The red's above the blue. And here we can see the green's positive there. Okay. If we made it plus instead, you could do the same thing. You could say, oh, here's red, here's blue. Green is what you get when you add them together. Here, the blue is negative. Or, sorry, the blue is positive, the red is negative. The green is somewhere in between, near 0. Blue doesn't exist over on the left, so green doesn't either, because we said since it has to be in the domain of both the red and the blue for it to be in the domain of the green. Okay. So, let's go on to some more. So that one's pretty straightforward. Composition is a new operation, and it's one of the most important ones, I'd say, because it allows you to take simple functions and put them together. Our transformations that we were doing before, those are a form of composition because we are combining like a shift to the side and a stretch and a flip and all these others with a function like a square or something. And so we use this little circle symbol. I didn't like this circle symbol at first, right? F of g of x. That's what it means. It means we're plugging the g into the f. So wherever we see a variable in f, we replace it with g. So you can use either one of these notations. I'm fine with it. You can call this fog if you want. I won't complain. The circle's really good when you have like a whole bunch of functions composed one after the other, because then if you try to do it with parentheses, you get so many parentheses it gets messy. But anyway, we're going to get from the functions x squared and x minus 3, we're going to do the compositions in both directions. F of g, g of f. And it says find their domains. I'll tell you right now, these functions both have domains of negative infinity to infinity, and there's no problem with like zero denominators or anything like that because it's not division. So the overall domain will also be negative infinity to infinity. All right, but let's see how this works in practice. All right. F of x is x squared. G of x is x minus 3. So we said, what is f compose g? F circle g of x. This is the same as saying f of g of x. So g of x is a unit. We say, okay, let's look at the f function. The f function is x squared, and we are plugging the g function into the f function. So that means I write out f, wherever I see an x, I put in parentheses x minus 3. So this would become x minus 3 squared. And you can expand that if you want to. I don't really need you to for this. What if we go the other way? G of f of x. Or g of f of x. Well, that would become, so we would take the f of x function, which is x squared, and we would look at g, and wherever we see an x, we'll write x squared. So it would become x squared minus 3. Now, I always say when I plug in, I use parentheses. In this case, we can just drop them. They don't really contribute anything. So x squared minus 3. These are not the same. Composition of functions is definitely not commutative. And so what's really happening here, I described a function as looking like a machine. This is how I've always pictured them. Well, if I have an f function and a g function, which I say is I take the x, I plug into f, and something comes out that's called f of x. I take that f of x, drops into the g function, what comes out is g of f of x. And then you could say this new function, g of f of x, well, I mean, it is a new function. And so the point is, if we were repeatedly having to do two different operations in a row, like first you have to square, then you have to minus 3, we can combine them, or vice versa. We can combine them into a single function and save computer space because we don't have to write out so many steps. So, it said, what is f of g of 5? Well, that is the same as f of g of 5. And I look at g of x is x minus 3, so that's f of 5 minus 3, which is f of 2. Becomes 2 squared, or 4. Now, did I need to do that? No, I could have used this combined function right from the beginning. F of g of 5 would be 5 minus 3 squared, which is 2 squared is 4. It's the same thing. It's just a matter of how you choose to write it. But a lot of times, once we've combined the functions, composed them into a new one, we don't even think about the other ones anymore. On the other hand, if you were given this from scratch, it might be worth decomposing it and saying, well, first you do x minus 3, and then you do squared. And that happens, that's another thing that happens in Calculus Odd. It's called the chain rule, which is saying, if I've got a complicated function, I can break it up into its component pieces and do them one at a time, as long as I know this precise rule. I think the other one was g of f of 7. Yeah, let's do g of f of 7. Alright, so g of f of 7. I'm just going to skip to the end version. It was x squared minus 3, so it'd become 7 squared minus 3 is 49 minus 3, or 46. But if you did f first, plug in 7, and got the 49, you would then do 49 minus 3 to get to 46. Okay. So let's do one that's a little harder now. F of x is square root of x. G of x is square root of 2 minus x. Let's find these compositions. And when we find them, we've got to find their domains, which can be tricky. Because we have to find the individual domains, and we have to find the combined domain. So let's see if we can figure out how this works. This is one of the trickier parts, and it's one of those things where, well, I think I can... I hope I can explain it all right, but if you don't understand it, please feel free to come by and ask. So if we want... Okay, so first let's list the individual domains. Domain for f is 0 to infinity. Domain for g is negative infinity to 2. So then I say, okay, what is f of g of x? Well, let's just do this formally at first. Let's just plug it in and see what it would give us. We would get f of square root of 2 minus x. And then we'd plug that 2 minus x in here. It would be square root of 2 minus x. Can we simplify that? Yes, because we could rewrite that as 2 minus x to the 1/2, not negative, to the 1/2 to the 1/2, which would be 2 minus x to the 1/4, or 4th root of 2 minus x, whichever way you want to write it. These are equally good. Now, what's the domain? Okay, now let's look at this. Domain of f of g would be, so if I look at this, I say it's an even root, so it'll still be negative infinity to 2. We would also have to make sure that the first function worked as well. If for some reason this square root somehow got canceled out, or an extra square root got added or something, we'd have to be careful to make sure each step worked. So it's like this. If our first function is g, and the machine breaks because x is not in the domain of g, then we don't even check whether it's in the domain of f. On the other hand, with the f part, it kind of takes care of it in the combined form. This is hard to explain. I would wish I had a really clear way of saying it. It's like there's two steps to the domain. We have to make sure it's in the domain of the first machine, the first inner function, and also that the thing that comes out of that is in the domain of the second function. But you can usually check that just by looking at the final form. So I guess what I would say is for domain of f of g, it would be the domain of g intersect with the domain of f of FOG, where this is just a formal process. And by formal, I mean we just didn't even think about whether it made sense. We just plugged it in and see if it worked. And so it could be that yeah. All right, so yeah. So what I'm saying, I think what I'm trying to say here then is that once you've computed the f of composed g, you have to cut out anything that's not in the domain of g. But you don't have to worry about the domain of f. And that's because g is the first one that's taken care of. So you have to check that, the one that comes first, but not the one that comes second. So the one that comes first and the final form. Again, that's a little hard to explain, and I'll think about if there's a better way to do it that makes it more clear. But let's look at this. Okay, so g compose f of x would be, all right, g of f of x was square root of x, so square root x would equal square root of 2 minus square root of x. All right, so this would be an example of what I was just talking about then. F of x is our inner function. And domain of f is 0 to infinity. And then g compose f is our combined function. Domain would have to be 2 minus root x is greater than or equal to 0. Which would mean, let's see, how do we do that? 2 greater than or equal to square root of x. How do we solve that? Square root of x has to be less than 2. Okay, so we know x has to be positive. So that means x is less than or equal to 4. So the combined domain g of would be 0 to 4. I guess I should say greater than or equal to 0. All right. So yeah, so the domain here of the combined function we had was 0 to 4. If there were anything in this that was not in the domain of f, we'd have to cut it out. But in this case, that doesn't cause us any problems. Okay. Now we can also compose a function with itself. F composed f would be the f of square root of x, which is the square root of the square root of x. And once again, that is x to the 1/2 to the 1/2, or x to the 1/4. And so the domain here would be 0 to infinity. We can also compose g with itself. I guess I should say of x, although if you leave that off, most people won't care because they can tell what you mean. The only problem would be if there's more than one variable. Okay, so let's do this. G of x would be g of square root of 2 minus x, which would be square root of 2 minus square root of 2 minus x. I don't think there's any way to simplify that. All right, so domain of G by itself is negative infinity to 2. And then the domain of G composed G will give us 2. Well, let's not use an equal there. 2 minus square root of 2 minus x greater than or equal to 0. Okay. Let's see if we can solve that. So 2 greater than or equal to square root of 2 minus x. Can we square both sides? Okay. Now, squaring is tricky, but we are saying since both sides of this are always positive, the square root always gives a positive number, and the 2 always gives a positive number, so we can square both sides. Because the rule always was we can't multiply by something that might be negative. But both sides of these are always positive, so this should be okay. 4 greater than or equal to 2 minus x, which means x is greater than or equal to negative 2. So the overall domain of G composed G would be negative 2 to positive 2. Alright, and since this is a video, I don't have to feel bad about rushing through because you can always just pause if you need to check stuff. Alright, we got 3 functions. Let's do a 3-way composition. F, compose G, compose H. So that would be F composed G of H, which is x plus 3. Which is F composed, let's see, well, plug in the x plus 3 to the G function. G is x to the 10th. So x plus 3 to the 10. Which is, then F is x over x plus 1. So it would become x plus 3 to the 10th over x plus 3 to the 10th plus 1. And now the order of the functions, we say if the H, the first one is x plus 3, its domain is everything. G is x to the 10th, its domain is everything. F is x over x plus 1. If this thing could be negative 1, we'd have to watch out. But since it's a 10th power, it can't be negative. So the domain would be all real numbers. Okay, I'm going to have one more problem, an application here, a modeling problem. And this is in the textbook, and it's worked out, so I'm just going to read it here. But you got a ship traveling 20 miles per hour parallel to a straight shoreline. The ship is 5 miles from shore. It passed a lighthouse at noon. And so we're going to try to get a function for each step. We're going to say let the distance be a function of time. No, it's a function of distance. Sorry, not time. Wait, hold on. What does it say? The distance. Oh, sorry. The distance to the lighthouse as a function of the distance the ship has traveled along the ocean. And then the distance of that distance, function of that distance, as a function of time. And then combine them. Picture will clarify. Let's do that. And this is another one of those common calculus setups. Certain problems that just, they test certain calculus skills well enough that they become kind of standard. Plus, the same author wrote the Precalculus book and the Calculus book, so he knew what he was preparing students for. So, let's have a boat here. Ship. And it is traveling parallel to the shore at a speed of 20 miles per hour. Now, let's say over here there was a lighthouse. Something like that. There's a bright light that way. And we said, okay, they gave us some parameters. They named them. They said the distance from the boat to the lighthouse is S. So we'll call that S. And so then, and we said at noon, it was 5 miles. Well, it's been 5 miles out the whole way. Since it's parallel, distance will always be 5 miles. So this is 5. My S looks too much like my 5. Let's see if I can... try to draw the 5 really angular. Okay. So, what happens in these sorts of problems usually is you've got different quantities related to one another, and you want to try to come up with some geometric relationship between them. In this case, the geometric relationship is the Pythagorean theorem. This was at noon. So the distance traveled here, we'll call that D. They told us to call that D. Since we're at 20 miles per hour, D must equal 20 times T. And that's our G of T. S, and so see the thing is, you might not be able to figure out immediately, oh, what is S as a function of time? I'm not sure. But if we do it in two separate pieces, first find D as a function of time, then find S as a function of D. S is equal to, Pythagorean theorem here, square root of D squared plus 5 squared, or square root of D squared plus 25, which would be, and we said they want to call that F of D. F is a function of D. So we want to write what is S as a function of time. Well, we would first take time. Apologize, someone honked their horn outside my window. First take time, plug it into G to get distance. And then we would plug that into F to get the diagonal distance. That's what's happening, right? T gives us D, and then D gives us S. The first one was G, the second one was F, so it's F of G, which would then be F of 20T. We'll then plug that into this F function. It would become square root of 400T squared. Well, let me write it out in parentheses. I should do that. 20T squared plus 25. I would expand that out as square root of 400T squared plus 25. And I know it's tempting to say, let's take the square root of both. That doesn't work. That's Pythagorean theorem says that doesn't work. You cannot split a square root across a sum. If these things were multiplied, we could split them, but they can't because they're added. So this is our simplest form. And so what happens in calculus is then they'd say, well, how fast is the lighthouse? How fast is the light spinning compared to where the ship is, or something like that? Calculus takes these geometric setups and then says, well, what happens when things start changing? How fast are the changes related? They call them related rates problems, because they're like, how does the rate of one thing relate to the rate of the other thing? In this class, though, the setup is what we are focused on primarily. Here it is. Alright, that is it for this lesson. Please email me if you have any trouble with it, or come by my office hours. Thank you for listening.